Welcome to this masterclass on momentum, a fundamental concept in advanced classical mechanics. We will analyze the quantity of motion in objects, derive the core relationship between force and momentum change, and explore the laws governing collisions. Our study is divided into 4 parts. First, defining linear momentum, followed by the derivation of Newton's second law. We then explore the Impulse-Momentum Theorem, and finally, conservation principles. Momentum is defined as the property of a moving body that determines the time required to bring it to rest under a constant force. It's the combination of an object's mass and its velocity. Think of it as the oomph an object has while moving. Mathematically, momentum, represented by the vector p, is the product of mass and velocity. Since velocity is a vector quantity, momentum also has direction. If an object stops, its momentum is 0. We derive the standard SI unit for momentum from its definition. P equals mass times velocity. Mass is measured in kilograms and velocity in meters per second. Thus, the unit for momentum is kilograms times meters per second. From a dimensional perspective, the formula for momentum is derived from the base units of mass, length, and time. This tells us that momentum is fundamentally about the distribution of mass over distance during a time interval. Momentum is a vector quantity, meaning a change in direction means a change in momentum, even if speed remains constant. For example, a ball bouncing off a wall at the same speed still undergoes a massive physical change in momentum. For a constant velocity, momentum is directly proportional to mass. This means a linear relationship exists. Doubling the mass of an object will exactly double the force needed to stop it at the same speed. Similarly, for a fixed mass, momentum is directly proportional to velocity. This linear scaling is why a light mass object, like a bullet, can be incredibly destructive due to its extreme velocity. Newton's original statement of the second law is deeper than the familiar F equals ma. It states that the rate of change of momentum is directly proportional to the applied force. This applies even to objects with changing mass, like rockets. We begin the derivation by expressing force as proportional to the derivative of momentum with respect to time. By defining the international unit of force, the constant of proportionality, k, becomes exactly 1. In the second step, we substitute the definition of momentum, mass times velocity, into the force equation. Our goal is now to perform the calculus operation of differentiation on this product. Applying the calculus product rule gives us the derivative of mass times velocity. This yields mass times the derivative of velocity, plus velocity times the derivative of mass. This is the universal form of Newton's second law. In most classical situations, an object's mass remains constant. Therefore, the rate of change of mass is 0. This simplifies the equation significantly, causing the second term to vanish. Since the derivative of velocity with respect to time is acceleration, we arrive at the familiar formula: force equals mass times acceleration. This derivation shows that force is the tool used to change a body's momentum over time. Next, let's explore the concept of impulse, represented by J. Impulse is the total effect of a large force acting over a very short time. This is often described as a hit or a blow, like a bat striking a ball.
Mathematically, impulse J is the average force multiplied by the time interval of the impact. It has the same dimensions and units as momentum, which hints at a physical connection between the two. The Impulse-Momentum Theorem links these concepts, stating that the impulse of the net force on a body equals the change in momentum of that body. This explains why following through in sports is effective.
To derive this, we start with Newton's second law, where force equals the rate of change of momentum. We rearrange this to show that force multiplied by a tiny time interval equals a tiny change in momentum.
Integrating both sides over the duration of the impact, we find that the area under the force-time curve, the impulse, is exactly equal to the change in momentum. Impulse and momentum change are two names for the same physical reality. Moving to conservation principles, the law of conservation of momentum states that in an isolated system, the total momentum remains constant, regardless of internal interactions. An isolated system means there are no external forces. The total momentum of a system cannot be changed by internal forces because they cancel out according to Newton's third law. Only external forces, those originating outside the system, can change the total momentum.
The proof of conservation starts with Newton's third law. The force of A on B is the negative of the force of B on A. This sets up the balance required for momentum conservation. We then express these forces as the rate of change of momentum for each particle. This shows that the change in momentum of particle A is the negative of the change in momentum of particle B, ensuring balance. By moving all terms to one side, we see that the derivative of the total momentum of the system is zero. In physics, a zero derivative means the quantity is constant over time. The proof concludes, the total momentum before an event must equal the total momentum after that event. This is the final result of the law of conservation of momentum.
Collisions can be classified based on energy conservation. In an elastic collision, both momentum and kinetic energy are conserved. Objects bounce off each other perfectly, typically seen only in atomic interactions. In an inelastic collision, momentum is conserved, but kinetic energy is not. Energy is lost, usually as heat, sound, or through permanent deformation of the objects, as seen in car crashes. A perfectly inelastic collision represents the maximum kinetic energy loss, where the colliding objects stick together. The total initial momentum is conserved, but the objects move with a single, common final velocity.
Recoil is a direct application of momentum conservation. Before firing, total momentum is zero. When the bullet gains forward momentum, the gun must gain an equal and opposite backward momentum to keep the total at zero.
Rocketry is a classic application of momentum, where mass is not constant. Rockets propel themselves by expelling hot gas or exhaust at high speed. This gives the rocket an equal and opposite upward momentum kick.
In 2 dimensions, momentum is conserved independently along the x and y axes. When solving real-world angled collisions, we must break the momentum into horizontal and vertical components, applying the conservation law to each separately.
Engineering car safety relies on the Impulse-Momentum Theorem. By increasing the impact time using crumple zones, the average force exerted on the occupants is significantly reduced, which helps prevent serious injury.
Kinetic energy and momentum are related, but they are not the same. Kinetic energy is proportional to the square of momentum. This means a small increase in momentum results in a disproportionately large increase in kinetic energy.
Let's review common fallacies. Momentum is not the same as force, it's a measure of mass in motion. Also, a stationary object has zero momentum, regardless of its mass.
This elastic logic map shows that in a perfect elastic collision, the relative speed of approach equals the relative speed of separation. This means no energy is converted into non-kinetic forms during the impact. In sports, the follow-through maximizes impulse. By increasing the time of contact between a bat and a ball, the final momentum imparted to the ball is maximized, resulting in a higher exit velocity. Finally, we check the physical consistency of the Impulse-Momentum Theorem using dimensional analysis. We find that the units for impulse, force times time, match the units for momentum, mass times velocity, confirming the physical relationship. This mastery summary table provides a quick reference for the 4 essential formulas we have covered: the definition of momentum, Newton's second law, the Impulse-Momentum Theorem, and the conservation of momentum. Thank you for joining this detailed video on the physics of momentum. This concludes our module on classical mechanics. We hope this video has provided you with a deep understanding of this fundamental physical property.